Welcome back to another OpenGL GLSL tutorial, and this time we are going to take a look at shadows. It was requested from me several times, and I'm sorry that I did wait so long to actually get around and make a tutorial about shadow mapping, but here we go. So shadow mapping is actually for shadowing, as you might probably guess. And as you can see, I have a little example program right here, so we will end up in the end of this tutorial. And most of the scene is pretty static, the light isn't moving either, it's somewhere up there, though I didn't draw anything at the place of the light. But from the specular light and the shadows, you can probably guess that it's somewhere there in the blueness. Okay, so most of this scene is pretty static. I added also a dynamic object right here just to demonstrate that it actually works for dynamic objects as well. But the basic idea is that we are just going to draw a simple static screen. We don't actually need dynamic screens for now. But of course you can draw skeletal animation and anything you would like. As you can see, it's animating the shadow. And also there is a self-shadowing, I guess, or maybe not. Yeah, there is some kind of self-shadowing. It's not the best shadow which you can make, but it's kind of okay. Shadow mapping is quite of a expensive operation, meaning that you need a lot of processing power just to make the shadow mapping work. I used also PCM, this is a percentage close filtering, to make some kind of little soft shadow. It could be better by increasing the number of steps in the for loop. You will see later on and about the end of this tutorial. So yes, that pretty much was just a demonstration to see how everything is working. It kind of gives a mood to this entire thing. This shadow right here comes from that cube right there, center of the screen. And right here in the slide we don't actually have anything which has shadows, but just simple the lack of light. So if I just go somewhere approximately to the place of the light, where could that be? It was approximately like that. So not exactly, it's more like that. So there's the light looking at this direction. Okay, it's still not perfect, it's more above, isn't it? Yeah, almost. Anyway, so it was approximately at this position, so there is no light there because, this entire frustrum doesn't actually contain that position, and that goes to my next point. This tutorial will be only about the directional shadow maps. If you want to make, for example, a point or an omnidirectional, with another word, shadow map, what you need to do is actually taking several images with 90 degrees of angle in the projection matrix. So you take one there, you take one there, you take one there, you take one here, you take one up, you take one down, and you put it together to six shadow maps. You will see more precisely what these ideas mean later on. So for now I'm just saying, but later on I will exactly point where you should modify to make a directional, so non-directional, so an only directional shadow map. Yes, I'm pretty sure this should be enough from the demonstration, so let me just open up a little bit of presentation about how this entire shadow map works. It's a very simple idea, it's a very simple idea, but it takes a little bit of time to understand its simplicity. So stay tuned, I'll open that presentation up in a moment. Welcome back to another OpenGL GLSL. Alright, so let's just quickly start in game and show you the little frames I made. It's not a lot, it's just the basic idea. So let's actually start the most basic thing about shadow. What is a shadow? So basically shadow is just the lack of light. It's nothing more, it's nothing less. Where the light doesn't actually hit anything, it will be shadow there. Wherever the light hits something, it will be light there. And this is about my first little layer, which is just stating the obvious. If the light, which is the light source right here, the light bulb, actually hits some of these pixels, so I don't know, it hit, let me just change this. So it hits this pixel. We don't actually see anything, do we? So if it hits this pixel right there, then it will be lit. But if it doesn't hit this pixel right here, it will be in shadow. Pretty simple stuff. I'm pretty sure you agree with me on this one. So let's go to the next point. We can express this on another way. If we would go into the position of the light with the camera, so let me just draw a camera here. It is a camera. It's a triangle, but it wants to simulate the camera. If we go just right here at the place of this light source and we take an image, then whatever we see basically will be in light, and whatever we don't see is in shadow. I can actually show you this one. This is how I position into the right position. So if I just go somewhere here where the actual light source is, we will not see any shadow if I could just go into exactly that position. Okay, I'm not exactly that position, but okay, so just trust me on this one. If you are exactly on the position of the light, you will not see any shadow. Of course, you have to move exactly to the position of the light. Right, so if we just go into here to the light position and we just take an image, then whatever was there on that image will be lit, and everything other which wasn't on that image will be in shadow. This is the basic idea. So we can actually write an algorithm from this one. Let me just throw it here. So the algorithm is basically going to the position of the light and rendering to the screen, and somehow we remember all of the pixels which were on the screen. And then we do a second pass. It will be basically mostly on the shader, and this time if we remember that point which we are currently rendering, we render all of the point, and if we remember that point, that will be lit. And if we don't remember that point, this will be only getting the ambient light, as you can see here. If we remember that pixel position, so we seen earlier that pixel position whenever we were on the position of the light. Of course, we are in the second pass, we are the position of the camera. So if the camera is here, then we render it from here, render everything, and if we remember, if we seen that pixel, that will be lit, and if we didn't remember, that will be on shadow. Now the stuff is we have to remember the pixel. How can we do that? Your first idea may be something like creating a vector and put all of the pixel position into it, and it can actually work if you do it correctly and all of the shadows, but the shadow mapping basic idea is to use the depth texture or the depth buffer to actually remember the pixel position. Let me see if I wrote in here. So in the first pass, we are just going to render from the light position. I've already said that. And then we are enabling the GL depth test when we are rendering from the light position. Actually, we usually have the GL depth test on, so we don't actually have to manually enable it, but so enable the depth testing. And what the depth testing basically does is only leaving to the closest pixel on the screen as well as in the depth buffer. So if we render this cube right here, then we get all of the closest pixel to the screen. So basically all of the pixels which we have seen. So then we can use this information later on to find out which pixel did we actually see and which pixel did we actually not see. So right here, as you can see, we get, for example, 0.5 for this pixel of the cube from the perspective of the light, and we just save this into a depth buffer, or more precisely with the help of the frame buffer object we are going to save this on a depth texture because that's easier to handle. Then we are in the second class, we are going to again render the geometry, and then for every single point, every single vertex, we apply the same transformation, basically to go into the position of the light. This is pretty simple. We have the GL model view projection matrix, actually not GL because we are using our own matrices, but we have the model view projection matrix of the light. We can get the model view projection matrix of the light by pretty much just remembering when we have gone to the position of the light, we remember what was that matrix which brought all of the vertices there. So we remember the model view projection matrix. And then we render with that model view projection matrix in the first pass. But in the second pass, we use again that matrix and bring every single vertex into that position. And for example, if we render this same pixel again, same vertex more precisely, which is interpolated, so it becomes a pixel right here, or fragment, then because we applied the exact same transformation on this, like we have applied in the lighting, we pretty much go into this exact same position. So it will be 0.5, this distance, both in the depth texture, which we have created, and both in this value, which we have just transformed. But, for example, if I just transform this pixel right here, the close value was 0.5 right here, approximately, so right here, this is 0.5. And the far value is, I don't know, 0.8, for example, which is farther away. So that tells us that this pixel right here in shadow, because the distance from the light position is farther than the distance in the depth texture. This is the basic idea, and once you get your head wrapped around this idea, you will understand the entire thing which we are going to do. This is the most important idea of this entire shadow mapping process. All of the others are just implementation issues. So let's go and see what else I made here. So here is that figure a little bit bigger size. So in the shadow map, you will see this position right here, which is 0.5 in distance. But whenever you transform all of the vertices and you just send them onto the fragment shader, you will notice that the distance from the light's position right here, the distance is 0.8, which tells us that this pixel is in shadow. But if you will just do with this pixel right here, this pixel's distance from the light originally is, for example, I don't know, 0.3. And again, when you do the same calculation, it will be 0.3 again. This is the hardest idea of this entire thing. So once you understand how this works, you will understand the entire shadow mapping. Okay, and let's go. Of course, we have a little problem, which we will go into later. So I'm going to actually start from the tutorial about the matrices. So this program which I currently have already the matrices, our own matrices, to replace the built-in OpenGL matrices. I've already have some frame buffer object right here in the code. So if I just do a search for it, frame buffer object, as you can see, we already had the frame buffer object, and actually we already initialized this frame buffer object. And yeah, that's pretty much it. And I'm just rendering a simple monkey, and you can see the result if I just run this program. As you can see, this is just the basic program, nothing really interesting in here, or nothing which you have not seen yet. Just the basic program with the 3-dimensional camera, the pair fragment lighting, and that's pretty much it. I also have a quad renderer right there, which we are going to use to test out some things. And did I use the quad rendering? Apparently this should be something about post-processing tutorial maybe. I don't know, I'm going to basically step all of this stuff. I'm going to start off from a program which we are already familiar with. But most of the stuff we're going to just delete it right from here. Okay, I will say let's start coding, because this tutorial will, I believe it will be a long tutorial. So my first step is to actually model something which we can test out the shadows with. So I'm just going to open up my Blender. I'm going to use my old Blender, but it will just work with the new Blender or whatever Blender version you are actually want to use. So what I'm going to do is just create a simple plane and add some objects to it. So I'm just going to go mesh plane. I just resize it. I'm also going to add some random objects to some random places. I know right here. I'm also going to add a UV sphere. Okay, this UV sphere will be here. What else can I add? I add a monkey object, so I'm just going to move this monkey object here and rotate it on the X. I'm just adding random objects so we can test out the entire shadowing thing. Let me add a cone. And let me put it up here. Okay, what else do I have? Cylinder, why not? So I'm just going to put a cylinder here. Let me put a few more spheres. Don't actually have to be on the plane. This one will be a little bit above the plane. Okay, good enough for me. So I'm just going to save this out. I'm not actually going to use the blend format, although in theory you could use the blend format, but there is some modification we still need to do with the simp model loader. I'm just going to export it out as an object file because that's easy to work with. So I'm just going to go to export, and I'm just going to go into the position of the current project folder, which should be OpenGL shadow tutorial. That should be it, and shadow.obj is just as good name as any. I'm not going to export out normal, so it will going to smooth it. We don't actually need UV coordinates, NURBS. Materials can stay, though I don't actually have materials, everything, just the plain old gray. Anyway, so I have a shadow.obj, and let's actually load this shadow.obj. I'm just going to load it instead of this test.blend, which was this monkey head. So shadow.obj. And if I compile this program again and run this, we should see this modeled object which we have just exported. Yes, indeed, we see this modeled object. As you can see, everything has smooth normals, though it looks pretty funny for things like the cube. But that's not the point of this tutorial, to make a very realistic screen. Okay, the next step will be to find out a position for the light. So, for example, put the light right here for this position, and I don't know, look somewhere there, or put the light right here. So we have just somewhere to put the light. Of course, in a real life application, you will just put the light to a position read out from the 3D object format. But for now, this is just a demonstration. I'm just going to do it manually. If you have followed my tutorial, you know that I have this camera.age and camera.cpp file, and this is my three-dimensional camera which I use a long time. This has a few functions like get location, get pitch, and get yaw, and I'm just going to write out these positions in the OpenGL file so I know where to put my light. So let me actually go to somewhere, doesn't actually matter in the display function, it is just as good place as any. So I'm just going to write out cout and write out cam.get location, which returns a three-dimensional vector which has an overloaded binary shift operator or cout operator or iostream operator, whatever you want to call it. So pitch and so it can write out the entire structure. Alrighty then, if I just run this program, then we are going to see the exact position. Let me run this and move the position which seems approximately right. Let me move approximately here. This is just as good place as any. So right here we see the position of the light, which is minus 1.9, 11 and 21 and minus something. So I'm just going to put this into a vector right here so we know where the light is, and later on we can reference it and we don't have to hardcore those values. So I'm just going to create a vector 3D and light position. The light position, too many O, position and two less I. Now it's right. Let me just write this value down. Actually I can just copy it and put a few commas between them. So this is the position, and let me make another vector 3D because as I said, this will be a directional light. We also need the direction of the light, so light direction. The light direction will contain actually just two parameters, the pitch and the yaw parameter. Let me actually copy these two values into right here as well. And in theory, if we are just going to go to this position with the view matrix and with this rotation, then we get back the same position. Let me actually test that out. But first of all, we need to remove this one. We don't actually want to write out. Okay, so this second part, what did this do? Whatever. So it's rendering a texture to the screen. We don't actually want texturing right now. We are not doing post-processing of any kind, and this will just confuse us. And we are rendering to the texture here. I don't actually feel like rendering to a texture, so I'm just going to delete this bind frame buffer object, and we should be directly rendering this rendering to the screen. So let me see if the program still compiles and it still gives the same result as it did previously. I hope so. Yes, it does give the same result. That's pretty cool. That is exactly what we need. Alright, let's see what else. Let's try to go into the position. So I just delete the camera and manually go into the position of the light. So first of all, we don't need GL function. We have a pipeline right here. So pipeline.rotate x. And how much we are rotating on the x? This is in the light direction, right direction.x. Okay, and we need a rotate y, which is on the light direction.y. Let me just open up the CPP file so you are seeing what I am doing. Right here, I'm rotating x with cam pitch, and I'm rotating on y on cam yaw. Yeah, whoa, whatever. And then I'm going to translate to the position of the light. So let me just using the pipeline.translate, and I'm going to translate light position.x and similarly to the y and the z. So right here y, z, and here y. Okay, but there is one thing, this will going to work because I have the view matrix binded right here. But let's go back to the model matrix right here. Model matrix, just to make sure that most of the time, oops, I already have a model matrix right there. So what I did is basically go to the camera's, go to the light's position and then rendering to the screen instead of using the camera. I hope this should go there, and if it did, then we need to get out the depth values. That's exactly what we needed. This was the same screen as we had previously set for the light's position. I'm actually going to make a function to get the depth texture. So I'm just going to make a function called, what should I call it? I should call it get image from light position. Okay, this is a pretty long name for a function, but just to make sure you're pretty familiar with what this does. So I'm just going to copy this part right here without the cameras. So this part, I'm going to go to the position of the camera, and I'm going to load the identity and the view matrix stuff right here. And then I can just use this get image from the light position. So let me call it right here, get image from light position. We are not getting any image yet. We are going to get an image right here by rendering to the depth texture. What do we need to render to the depth texture? Well, first of all, we need a depth texture. So let me just go into the initialize, and we already have a depth texture, but I'm going to want to create another one because this one is the default depth texture. So we are going to use this depth texture whenever we want to, I don't know, use the render texture with, so use the frame buffer and use the depth texture. But sometimes the depth texture for the shadow map will not be the same size as the screen, while the depth texture for the screen should be always the same size. For now, I'm going to just create the same one. So depth texture, or what should I call it? I should call it shadow map, just to make sure you just to make sure we understand what this variable is. This is the shadow map. This shadow map will contain the depth. For now, this is just exactly the same as the depth texture. So 640 and 480, which is our screen size, and it is a depth texture. Cool. Then let me go right here to the get image from light position. And after we go to the light position, right here, I should write it, go to light position. Perfect. Then I'm going to bind this frame buffer. So we are going to render to this frame buffer. So GL bind frame buffer, and I'm just going to bind to the frame buffer, GL frame buffer. And the second is I'm going to bind the FBO, which is our frame buffer object, which we have created in an earlier tutorial. Defaultly, the attachment is depth texture and a color attachment 0, but I'm going to change this very soon to the shadow map because we are wanting to render to the shadow map. To render to the shadow map, I'm going to copy this because I don't feel like typing it again. This function is going to use our shadow map as the target for rendering. So basically, we are telling here that for our depth attachment, we are going to use the shadow map which we have created. So I'm going to render to the shadow map. And yes, we are going to render to a shadow map, and we need to use a shader right here to render to the shadow map. And we could use this shader right here because this will just as well as any other, we are going to render to the shadow map. But just for the sake of performance, I'm going to write another shader which has nothing else to do but just put out the render, put out the pixel right there. Without any computation, without any calculation, just put out the pixel where it should be. So let me just create two shaders. The one shader will be called, what should I call it? Simple shader, because I hope there is no such shader. Yeah, perfect. And I'm going to create another one, simple shader.frag. Oops, I created the fragment shader, didn't I? So simple shader.vs. So we have these two shader, and I should probably copy and paste some stuff to make everything a bit quicker. So I'm just going to use this quad renderer.frag and vs to create the vertex and the fragment shader, though there will be a few differences. Right here in the simple shader.vs, by the way, I should probably set the shading language. I get a comment on that. I didn't even know that there is a coloring for shader languages. Anyway, so we need, what do we need? We actually need only model view projection matrix, because this is the only matrix which I use right here. We don't need varying variable or this attribute variable right here. As I said, this will be the simplest possible shader which you can create. This is pretty much what we have created in the GLSL tutorial number 1. So sending the vertex position, and in the fragment shader, what do we need? Is just writing out we don't actually need even that. What do we need in the fragment shader is we are just writing out a color. What color? Doesn't really matter. Whatever color you feel like writing out, but the fragment shader needs to write out something, so I'm just going to write out the red color. You can write out any color you wish. So yeah, this is the exact same code as in the GLSL tutorial number 1, except we are using our own model view matrix, except the building one. I hope I didn't screw that up because this is so simple that is unlikely. So I'm just going to create a shader class. So shader, and I'm just going to call this shader simple shader. This is pretty much what we're going to accomplish the first pass. The first pass, which if I just go back right here, rendering the depth values to the depth texture with GL depth test enabled. This is all which it, this is a simple shader which it will going to do. Right. So simple shader, and let's initialize this simple shader right here where I initialize the other shader. So new shader and simple shader.vs and the simple shader.frag. Did I use capitalization? Yes, I did. So let me put a capital S right there. Okay, I don't think I screwed this up, so let me just delete this shader as well at the end of the program, like I delete everything which I have created with new. And okay, so let me just use this simple shader, so simple shader, and I'm just going to use the function use shader, and at the end I just del the shader, so I don't use the shader again. Oops. So del shader, just to make sure that we are not accidentally render something with this shader which we don't want to render with this shader. Okay, and then we have to actually update the matrices, so let me use the pipeline.update matrices with the simple shader. No, it doesn't. So simple shader get program ID. Okay, and I'm just going to call the render scene function. I'm going to make another function which we're going to render a scene. Void render scene. Do we need this function? Okay, I'm not going to create another function. I'm just going to write here. But remember that if you have a big scene with a lot of objects, you want to probably create a function, because we are going to use this in two places. But because this is just one line, it would be just a waste of time to create that function. So I'm just going to use the, what was it called? The scene. Actually, let me copy this. Scene. And with the simple shader, just to make sure that our depth test is enabled, because that is the most important thing which I have wrote here, that GL depth test has to be enabled, because we only want to use the depth values. So GL enable GL depth test. Okay, so enable the depth test just to make sure that we have. Do we need anything? We should probably clear the buffer. So GL clear GL depth buffer bit. Alright, and we should bind a 0 frame buffer at the end so we don't accidentally render to the frame buffer. Okay, this seems okay for me. This is going to render to the shadow map, and then we should probably write out the values. Now great, because I have just deleted the part which can render to a quad. Probably I should quickly undo that from a program. Okay, so here I am. I just copied out the render texture to screen function from the earlier program, and let's just quickly go through what does it do. First of all, it disables the depth texture. Make sure just we enable it, GL enable, because we don't actually need depth texturing. We are going to render only a simple quad on the screen. Then it's going to set up an orthographic transformation matrix, which is just pretty much a 1 by 1 by 1 cube, which is exactly the same size as our simple quad. So it will just fill up the entire scene. Then I'm going to use this shader which we have created earlier. This is just a simple shader which rendering a simple quad on the screen. Let's see what else do we have here. I should bind another texture which is called not depth texture, shadow map. This was the name. So I'm going to render out the shadow map on the screen so we see the distances. And yeah, this should be pretty obvious. So let me just try to compile this and hope I didn't make too much mistakes. GL enable test. That sounds weird. GL enable GL nest test. Okay, I'm a little bit tired. This is my excuse to write stupid things. Okay, let me try to run this, and exactly we get, I don't know how good resolution do you see on YouTube, but as you can see, far objects are white, closer objects are kind of grayish, and closer the object, the more dark it is. So if you have a pretty good resolution, you see that here is a cube which is a little bit closer, and here it's closer than the background, and here it should be the most dark thing right here because this is the closest to the camera. Okay, it's hard to see, but it's kind of there. Okay, we have actually finished half of the shadow mapping. Okay, the easier half, but we have finished half of the shadow mapping. We have rendered something to the depth texture. Right, what else do we need? So next step in the shadow mapping is we actually need to create another shader which is going to do basically the hard job. So alrighty then, but first of all, before I start to make the other shader, let me just remember the model view projection matrix of the light. I'm not sure how clear is this, because first of all, when I hear the concept, it wasn't clear for me at all, but maybe I'm just that bad of shader programming. Now I try to I kind of understand how it's working. So the first step, we are going to transform everything to the light position and render from the light position. So we get, I don't know, for this screen we get something like, we are on the batch layer. We would get something like this. This is the plane, and here we have some cube right here, and I just want to make it quickly. Okay, so we have something like this. So this is the basic idea. So we render from the light position and we get something like this. Then we are going to render basically from the camera's position, so that, I don't know, camera is just right here, and it is completely different thing. But still, we are going to use the model view projection matrix of the light. So what that's going to result is that pixels, for example, right here, pixels which cannot be seen are going to transform similarly to the position of the light. So it will be somewhere here, but behind the cube, so it will be transformed right there. Okay, I hope this is clear, but if not, try to think about it or try to check out the link in the links in the description. I have a few good sites which help me understand the basic concept. But let's first of all go to and get the model view projection matrix of the camera. So we can very easily do that. We can actually get each of these separately. So right here in the get image from light position, as you can see, I already go to the position of that light. So right here, I could just use some matrices to get the position. I'm just going to create another variable right here. This will be a GLM matrix 4, and I'm just going to call this shadow matrix. The shadow matrix will be the model view projection matrix of the light. With a little bit of tweak, we will get into that in a moment. So I'll just write it right here, light model view projection matrix. So this is an important matrix because we need to use that. So in order to get this matrix, we need to obviously multiply together the model, the view, the projection matrix in the opposite order, by the way, and then we have the model view projection matrix. So let me actually get a few local variable right here. So mat4, and the first one should be, I don't know, model matrix. And let me make a view matrix, and let me make a projection matrix. And I get all of these matrices separately from this matrices or pipeline. The class is called matrices, but the instance is called pipeline. So get model matrix. I'm pretty sure this is the name for getting the model matrix, and this should be put right here to the initialization. And then I just get the view matrix right here, the view matrix, and then I just get the projection matrix, get projection matrix, and there we have it. We have three matrices: the model, the view, equal sign, and the projection matrix. So the shadow matrix is pretty much just we have to multiply all of them together. So in the opposite order, model, view, projection. So we start with the projection matrix multiplied by the view matrix, so view matrix, and finally the model matrix. Pretty cool stuff. We multiply them together. But that's not enough, and this brings me to my last layer in my texture. So I'm not sure if you are aware or not, but if you multiply a vertex position with the model view projection matrix, it's going to place that vertex into the something called NDC coordinate system. This is the normalized device coordinate. This is basically a space where the lower left corner is -1, and the left top corner is at 1 position. Similar to the texture where the lower left corner is 0, 0, and the top corner on the right is 1, 1. But there is a difference, obviously, and this is what gives us this problem. So as you can see, we have a twice as big normalized device coordinate. So what that means is that, for example, if we have a vertex in the normalized device coordinate with 0, 0, so right here we have a vertex right here, just transform with the model view projection matrix and it get here. Still a 0, 0 coordinate. It can happen, is it? And then we are going to write the depth value to the depth texture because we are writing to the shadow map, which is the name of our depth texture, to this 0, 0 coordinate. But when we access to this texture, the 0, 0 coordinate is actually not 0, 0 coordinate, but 0.5, 0.5 coordinate. So the center. Similarly, it is the center for the normalized device coordinate as well, but with different numbers. So this is the problem. We can easily convert that. So for every vertex, okay, so let me actually just say what we are going to do with this. So there is a vertex right here, for example. Then we are going to check the depth value of this, and we are also going to check the depth value of this vertex. So we are going to check the depth textures depth and the vertex depth. And if the vertex depth is less than the depth of in the depth texture, did I say it correctly? So if the vertex depth is greater, so the z coordinate of the vertex is greater than the value in the depth texture, then it's in shadow, else it's lit. So this is the basic idea, and we are going to access the depth value in the depth texture via the depth texture. So we are going to access the depth texture by the coordinates of right here. So if it is in the coordinate of this, then on the depth texture it will be on here. If the coordinate is -1 for a vertex, then it will be 0, 0 on the depth texture. So if we have a vertex somewhere, so we multiply by the model view projection matrix of the line, and we get a vertex position somewhere, get it here. Then we are going to first of all check the depth in the depth texture, and then check the depth in the vertex. Z coordinate is the depth for a vertex. And then we pretty much just compare them together, and if the vertex is farther away than what was in the depth texture, because it was the closest thing which we have seen, then it is in shadow, if I said it correctly. So again, try to go back into here and try to imagine what we are trying to do. But this is more of an implementation deal than the basic idea, than the idea of the shadow map. So what we need to do is convert this -1, -1, 1, 1 interval to a 0, 1, 1 interval, which is quite simple because we already did kind of conversations like that in other places. And to do that, we are basically just going to multiply the position by 0.5, so basically half the position. That will make the entire thing to -0.5, -0.5, so approximately here, and 0.5, 0.5. Then we are just going to push this with 0.5 on both axes, and it will be there. Just think about it. If you have any values right here, so for example we have -1, -1, we halve it, which is -0.5, -0.5, and add 0.5 to it, which will be 0, 0. This is the exact coordinate. So how can we accomplish that? Is actually using a matrix. Of course, we could go into our fragment shader and do this operation manually. So multiply the position by 0.5 and add 0.5 to it. But there is a simple way to do that with a matrix. Simple, I mean not simple for you, but simple for the computer. Because then, if we will do this manual trick, this multiplication and addition, there is one more additional step in processing this entire thing. But if we just incorporate this stuff into the matrix multiplication, it will going to work out. Don't click away if you don't quite understand this concept yet. You may get it later on through this video. So you just keep calm. I didn't understand it first either. So in the shadow matrix, we are going to create a matrix. So GLM mat4, and I'm just going to call this a BS matrix. This matrix will going to push the entire thing up. So going to make the -1, -1 to 1, 1. How that matrix is look like? It's a very simple matrix. So let me just write it here. Bias matrix, and we can access the elements directly. So the 0, 0 is 0.5, and let me just copy this and fill up this entire matrix. So 0 0.0, 0 0.0, 0 0.0. Let me just copy, we should increase these 2, 3, and let me go down. So it's a 4 by 4 matrix, as you can see. So we have this first line right here. So 1, 1, 1, 2, 2, 2. Oh, no. 1, 2, 3. That's what I should write here. 2, 3. And 3, 2, 1. Okay, the simple matrix will be that in the main diagonal we are going to have elements with 0 0.5, 0 0.5. On the right bottom corner we will have an element 1.0, and in the low line we are going to have element 0 0.5. Why do we exactly have this kind of elements? This should be obvious whenever you do the matrix multiplication. Remember that OpenGL uses column major ordering format, 0 0.5 times x, 0 times y, 0 times z, and 0 0.5 times the w. But the w, as you probably already know, is always 1. So what we are going to get is plus 0 0.5 times w, but the w is 1, so we get 0 0.5. You can play along with the other one, so y and z. For the last one, for the w, you're just going to get 1 because 0 times x, 0 times y, 0 times z, and 1 times 1 is 1. So you get this vector, which is exactly what we have wanted to achieve. Multiply the position by 0 0.5 and add 0 0.5 to it. This is basically the magic behind this bias matrix. Okay, but where should we multiply with this bias matrix? Because the matrix multiplication order matters. What I said basically to you is use the different order how you want to achieve the operations. So if you want to first of all apply the model matrix to the coordinates, you multiply it by the last. By the way, I just read somewhere that if you have row major format, which is pretty much how you usually have your elements of 3, 4, 5, 7, 8, 9, then you multiply it in the normal order, so model, view, and projection. So you multiply it in the right order, and you can give that to the OpenGL, because that will result the exact same value as if you would have a column major. So 1, 2, 3, 4, 5, 6, so and so on. So you would get the exact same result than if you have column major ordering and if you multiply in the opposite order. So when do we exactly want to multiply 0 0.5 and add 0 0.5 to it? In the very last step, when you have the normalized device coordinate, which is the -1, 1, 1, so this step, then you want to do that. But because we are doing everything in the opposite order, you first put here the bias matrix, or something like that. And that's right, we have our shadow matrix. One thing I should make sure that you know is that, of course, the model matrix could actually change. Why could it change? Because, for example, you use a translate. So for now, we will have just a very static screen. So this very static screen doesn't actually translate, rotate, or scale, or doing anything crazy. So the model matrix will be exactly the same as it was. But if you have multiple stuff, like, I don't know, you use the translate right here, then draw something, then again using the translate, then draw something, and then rotate, and then draw something, then you should calculate the shadow matrix every single time. So you calculate the shadow matrix right here after the translation, after the other translation, after this rotation. This is a very important thing, because without it, your shadow will not be correct. So make sure that you update your shadow matrix whenever either the model or the view or the projection matrix has changed. It's an important thing. Okay, so we have the shadow matrix right here. That's pretty cool, but what could we do with that? Let's actually start to make the shadow shader, which will be actually doing all of the hard work and do the shadowing. This time I'm not actually going to create lighting, so per fragment lighting, but only writing out if the pixel is in shadow or not. So pretty much writing out a white pixel if it is lit, and a black pixel if it is not. Of course, you can easily later on modify, and we are going to actually modify this in the end of this tutorial. But for now, just the sake of simplicity, I'm just going to create it very simply. So I'm just going to call this shadow shader dot fragment, and also I'm going to create a vertex shader. Shadow shader dot vertex shader. Let's start off with the vertex shader. What's the vertex shader need? we always need the vector free vertex, because this is our the input vertex, which we always need. The next, we need the model view projection matrix, because we want to render something to the screen, and for that we always need the model view projection matrix. So I'm just going to create a uniform mat4 model view projection matrix, just as always. I hope I didn't mistype that. Pretty much we don't need anything more from the default approach, but we need the matrix, so mat4, for the lighting. So what should I call it? I should call it light. Okay, so model view projection matrix, and I call it light model view projection matrix. I give a very long name and a very descriptive name to it. So this is the model view projection matrix of the light. So this is the exact same matrix we have. Actually, these are not our OpenGLs, but this is the shadow matrix right here, which I have created. Okay, then let's see, we need some varying stuff. Actually, one varying stuff should be sufficient for now, and this will be a vector4, and I'm just going to call this light vertex position. So if we transform the position, this vertex position, with this light model view projection matrix, that will be the position in the vertex, in the light space, basically. The void main, of course, we should probably turn on CG. Okay, main. And what do we need? We of course need the GL position as always. So position, and this GL position will be just the same as always. So the model view projection matrix times the vector4 vertex 1.0. So this is very basic stuff. We just putting everything where they should be, so into the camera's clip space. The next one, which is the actual important one, we said this light vertex position, so the light vertex position equals to the light model view projection matrix multiplied by the vector4 vertex 1.0. So right here, with this, I told the program, so OpenGL, that I'm going to put every pixel to the same position as my shadow map have been. Because, of course, in order to compare the depth with the shadow map, we need to have the vertices to the same position as if they were in the shadow map. So I'm just going to put this very long line to put everything to the light clip space. And that should conclude our vertex shader. So let's go to the fragment shader. The fragment shader actually has the shadow map, so uniform and sampler 2D. We will get back to this type in a moment, and I just call this shadow map. Alright, but there is a built-in function to do this comparison. So the comparison, which basically tells if it is closer or farther away than the pixel in the shadow map. And this function is actually called shadow to the PROJ, like projection. And this shadow to the projection actually don't need a sampler 2D, but need a sampler to the shadow. Just a formality to make everything work. But there is another way, which is the direct way. I'm going to show you that as well. We just use the normal texture, because I know that in some platform this function, the shadow 2D projection, might not actually work or might not actually perform so well. So I'm just going to show you the simple sampler 2D, so how to do the testing manually. But for now, I'm just going to use this function because it is a bit simpler. I'm going to also need a varying variable, so varying vec4, and the vector4 is this light vertex position. Okay, do we need anything else? I don't think so. So again, let me just turn something on. So void main, and let's see what does it do. So we have a function which I just deleted right there, shadow to the projection. PROJ, and this function is a pretty simple function. It's waiting for the shadow map, and the second parameter is this vertex position, and it will do everything for us. We don't need to ask anything. It will just do what it needs to. And let me set the let me get actually not the entire thing, but only the R coordinate. This will return a vector 4, but all of the components are the same, which is pretty much a grayscale image. So I could just get the R, G, B, or A components. Just as simple. I'm just getting the R component. This R components, so let me just write it here, are equal to 1.0 if the current pixel is if not in shadow. Not in shadow. And the R, so this result, so the R will be 0.0 if it is shadow. It's in shadow. Okay, so let me put this into a variable. So float, and I just call it the shadow value. And shadow value will be either 1 or 0, depending if it is in shadow or not. So let me just set the color to either black or white, depending on whether the current pixel is in shadow or not. So GL frag color, and this GL frag color is waiting for shadow value, and then I'm just going to write 1.0 for the alpha. So if it's either be black or white, and this is actually not good, is it? It is this. Like this. So I'm just setting the fragment color equal to the shadow value, which is either 1 or 0. And I'm pretty sure we are finished with the shadow shader. This is the first version of the shadow shader, which is pretty much the black and white version. So let me just exit some of this stuff right here, because we don't actually need all of this stuff. So we can use the OpenGL.cpp and the shadow shader stuff. Okay, so let me go to the display, and we don't need actually this rendering out the depth texture. That was just a temporary stuff. But what do we need is actually using the camera right here, because we want to use a camera, we like to use a camera. And also I should probably load the identity before I use the camera. So yeah, that's pretty basic stuff. This is how we use the camera. Okay, and let me just open up the shadow shader. So I'm just going to create another shader, this one called shadow shader. The shadow shader will be initialized right here to a new shader with the shadow shader dot vertex shader and the fragment shader with similar name. So shadow shader dot frag. Okay, I have it. Then let me just delete it before I forget it. So I'm just going to delete this shadow shader. Perfect. Then I'm going to use the shadow shader right here. So use shader and just del the shader at the end, just to make sure we don't accidentally do something we don't want to. Perfect. Let's actually fill up these values. So first of all, we need to fill up the vertex automatic, the model view matrix, projection matrix automatic. So we only need to fill up this light model view projection matrix. So let me go to the matrices at CPP and just copy one of these functions to make our life easier. So I'm just going to use this GL uniform matrix for SV function, and we are going to look for this light model view projection matrix right there. And then we are going to have already a matrix which we called shadow matrix 0 and 0. Pretty sure we give a shadow matrix or something similar to that. Shadow map. This is not where we give it. Right here, shadow matrix. So I'm just going to give the shadow matrix to the shader. What else do we need to fill up? We need the light. That's a varying variable. We don't fill up varying variables. Right here we have a uniform called shadow map. So let me use the GL uniform 1i, and the first parameter is this uniform stuff right here, and this one is called not this but the shadow map. So the shadow map, I'm just going to give our shadow map. Oh, what I'm doing, I'm going to give 0 to it and bind the shadow map right here. So GL bind texture, and I'm just going to bind it to the GL texture 2D, which is called shadow map. And I'm also going to activate the necessary layer, so GL active layer, and this will be just simple the GL texture 0, which is the first texture layer. The 0 is the same 0 as here, the 0. And then let's see, what do we need? We need to call the scene draw function. So let me just copy that from here. And also we need to update the matrices, don't we? So we need to call the pipeline.update matrices. And this is just waiting to the shadow shader get program ID. And right here, the shadow shader get program ID. And I'm pretty sure we got through the most important thing about shadow mapping, though this shadow mapping is a quite big topic and I can't really remember if anything I missed. Actually, only one thing I remember is that I have to go here to wherever I created the depth texture, so right here, somewhere in the init, and I should bind this image, so gl bind texture, gl texture 2D, and shadow map. And let me unbind this texture as well to 0 right here. And the thing is that we need to actually give another texture parameter right here, a similar texture parameter. Let me just copy this line, which is needed for this function which I have shown you, this shadow to the projection, as it will not work. So this is just one simple texture parameter which we have to change, and this texture parameter doesn't really do too much or too spectacular thing, but this is called texture compare mode. So let me just write it here, texture compare mode. And what do we want is texture compare R to texture. You don't really have to know what does it mean. Maybe it will be clear whenever we do the manual texturing. By the way, if this some reason gives you an error, don't give up. Come back in a So we are going to modify this in a moment, but first of all we should try to see if this program actually compiles. Probably it will not. Alright, some problem, not too much. So matrices have no member called getViewMatrix. That's interesting. So let me just go into the matrices and see if we forget it or what. Apparently we did forget. We have model matrix, we have projection matrix, but we don't have view matrix. That's a shame, but we can easily fix that. So get view matrix, and let me just copy this and go down here wherever we had this get matrices stuff. Okay, get here, matrices. Forget it along the way. So I'm just going to return. Let me just put return statement right here with from the view matrix stack. From the view matrix tab, the top matrix. Okay, that should fix one problem. Let's see the other one. So let me have my terminal. GL active layer. That should be GL active texture, isn't it? Let me go down and put GL active texture right here. GL active texture. Let's see the next one. The next one is in the next line. Bind texture so a capital T. Next one, program ID was not declared. This is because it's not program ID, but we are getting the ID for the shadow shader. So shadow shader get program ID. Let me copy that to here and here. Okay. Seems like we get most of them. Let's try to compile it and see what's going to happen. And let me try to run this one. We don't clear the screen somewhere, so let me just quickly try to clear the screen somewhere here, so anywhere. So gl clear, and I'm just going to clear the screen, so gl color buffer bit, and I'm also going to clear the depth texture, so gl depth texture bit. Gl clear the... Okay, let's see what's going to happen now. I wanted to write depth buffer bit, not texture. We have depth textures too, but I'm talking too much about the texture, and this is not a command, this is a binary OR operator. But now it shall compile, and we shall see something nice. Do we see something nice? We do see something nice. Okay, not that nice, but as you can see, we have shadows. We also have some more moire pattern, or whatever it's called. I think this is what it's called. This happens because of the finite resolution of the shadow map. But as you can see, where there are shadows, there are indeed shadows. Pretty cool. I didn't expect it to work so soon, but it actually do. Oh, so cool. Now what do we do about these patterns, and why are they appearing? They are appearing because we have a finite resolution shadow map. And that's not good, but we can't do anything about it because the infinite memory is not yet discovered. So we have to actually do something to make this pattern disappear, because I don't know, the player will get epileptic or something, and that will be not good. The simplest way to deal with this is to basically calling out the front faces. We haven't actually done face calling because it's a simple topic you can easily learn by yourself, but let me actually create a new layer, a new white layer, and see what this face calling actually means. So probably you already know, or maybe not, it doesn't really matter, that if you have an object right here, I have a triangle, then it will go, your fragment shader will go through every single pixel of this triangle, right? Because it, via the fragment shader, that's what the fragment shader does. It goes through pixels and then, I don't know, assign some color to them and calculate the lighting to them and so on. But it will not actually go through just the face which is facing toward you. So right here, this is facing toward you, but it will also go through the face which is not facing toward you, but facing away from you. So the back face, which is right there. So pointing right there. And this is true for every single object which you create with OpenGL. It will not only go through with the front face, this is the front face which is facing toward you, but it will also go through the back face. Now what you can do is sometimes, mostly for performance issues, but this time we are not only go for performance, but we are only going to go for better depth texturing. You can actually make disable either the front face or the back face, or actually both. So what that's going to result is that if you are watching this triangle from right here, so watching this from right here, then you see the triangle. But if you just go back to the triangle, then you will not see anything there, because the fragment shader won't even run for those pixels. This is pretty much double the performance in most cases, because it has to only run once for the this triangle, so for only the front faces and not the back faces. Why could that be good for performance issues? Of course, this doesn't make too much sense because you want to be able to move to the back of the triangle and see the triangle. But in case of closed objects, like for example, the simplest closed object which I can think of is a cube. Right here, a cube. Then, if you have collision detection and stuff like that, which pretty much makes it impossible to go inside the cube or go outside, depending on what you are doing, then you don't actually need to render, for example, if you are outside, the inside of the cube. Because whenever you go here, or go here, or go here, or go here, you will not be able to see inside the cube. So there is no reason to calculate a lot of stuff inside the cube. So like that pixel, and that pixel, and that pixel, and so on. Right, so this is about face calling, and how does OpenGL knows what is the front face and what is the back face? Why isn't that the back face which is facing away, and why isn't this the front face, or why isn't this the back face, or why isn't this, you get the idea. OpenGL using winding of the object. So if you define your vertices in counterclockwise, let me just think of that. So this is the first vertex, then we are going counterclockwise. The clock goes this way, right? So we are going then to here. Let me just draw. So we are going here, and then we are going here, and then we are going here. As you can see, I gone counterclockwise when defining. So this was the first, this was the second, and this was the third vertex which I have defined counterclockwise, I'm pretty sure. Then the front face is whatever is facing toward you. If you would do in the other direction, you would go to 1, 2, 3, and then this way. Now I have gone clockwise, right here, counterclockwise and clockwise. Then this is the back face which is facing toward me. Usually you don't have to worry too much about this stuff, because your modeling program will automatically deal with these kind of issues for you. So if you draw a cube in Blender, then it will automatically decide that the outer faces will be the front faces. Okay, so you don't have to really care about. You only have to care about when you're defining objects for yourself, like we have defined the quad or that cube stuff, which we have created, not by loading, but actually created with the vertices. I'm not actually sure if those vertex orders are okay, so try out the culling faces and see whichever face are in the wrong direction and whichever face is not in the wrong direction. You can enable the face culling by a function. This is not defaultly enabled. This is similar to def test. It is not enabled with gl enable gl cull face. This is basically how you enable it. This is similar to dev testing. You can enable it, you can disable it. Let me just disable at the end, because this is really not enabled for me. So we are enabled the face calling. You can also tell with a function which face should be called. So gl call face. You can either use gl front, GL back. This is the most obvious, this is the most used one, the back face calling, whenever the inside of the cube is cooled out, so not drawn. But you can also use something like GL front and back or something like this, which is cooling the back and the front face as well. I can't really think of a use for that, but probably there are. Okay, so we are going to cool the front faces now, which is a trick which I'm going to use. So let me go back here and create a new layer. So what is the problem is that, for example, right here, let me just draw a sphere and a plane. As you can see, this is my sphere and this is my plane. So let me actually do it kind of three-dimensionally. Okay, so we have the shadow right here, which is very correct, but we have this something called Moiré pattern. I'm pretty sure this is right, like Moiré pattern. This is probably a French physicist. And this Moiré pattern is a kind of interference pattern or something. This is happened for us because of the finite resolution of shadow map, but I've already said that, didn't I? So what we could do is not rendering the front faces. So we would going to render something like that. So we are not rendering the front faces. So we are not rendering pretty much this part of the sphere, and we're also not rendering the plane. And that will cause that from the front it will be lit. Why it will be lit? Because then the shadow map would contain this depth value, so a bigger depth value, and right here in the front, which is not rendered, there is a smaller value, which pretty much makes it lit. So this is the basic idea. So I'm just cooling the front faces, and that's all which we should do. And if I just compile it and run it, then we should increase the realism of the screen by much. As you can see, in the back face we still have this Moiré pattern. I'm not sure how to pronounce it, but in the front and right here from the plane it disappeared. Awesome. So there are ways to actually make it disappear. We will going to see how to make it disappear in a moment. But first of all, let's see that why is it so blocky. It doesn't look like a real shadow. This should be very, very smooth, and right here very, very smooth. But everything is so blocky. And the reason is that you have a small shadow map. So if I just come here, which is pretty much where our light position is, then for every single pixel there may be, so every single pixel on the screen, right, like I don't know, if I go this close, then one pixel is going to go for that one big block right there, and this is what makes it very blocky. So what we could do is actually increase the resolution of the shadow map. So I'm just going to go up here to wherever I define most of my constants, and I'm going to create a integer, actually not one but two, and I just call it shadow map width. And let's make it 640 by times 2. And also I'm going to make a shadow map height, and this will be 480 times 2. Cool, we have a new shadow map width, so this will be double the resolution. So let me actually go down here whenever I create the shadow map and passing the shadow map width and the shadow map height right here. So now we have a bigger resolution shadow map. Let me actually go back to GIMP and draw something. So we have the screen. Actually, let me just draw the screen to a smaller size. So we have the screen right here. We have the spheres and all the stuff right here. But I have created double the size of that shadow map. So I created this big shadow map. The problem is that although we have a very big shadow map, we're still going to render to a relatively small portion, which is 1/4 part of this entire shadow map, which is a problem. What we have to do is use a function which you probably are familiar with, but we haven't used it, which is called glViewPort. This glViewPort function, if you don't know, though probably most of the basic tutorial on OpenGL start with the usage of this glViewPort function, pretty much tells what part of the screen, or in our case frame buffer, do you want to draw in. So this viewport function is a pretty simple function. It only has 4 parameters. Let me just write it here how this function looks like. GL viewport. The GL viewport has 4 parameters. The first is the x, y coordinate, the first two. So 0, 0, which is pretty much the top, no, not the top, but the left bottom corner. So this is the 0, 0 in OpenGL. I'm pretty sure that it's not like in monitors. So this would be, I'm pretty sure this is it. And then the next two parameters are the width and the height. Actually, let me write x, y into here rather. So what this is going to do is makes your entire OpenGL render to this portion of the screen. So for example, if you have x, y right here, and you have this, I don't know, this big, then even though your screen may be this big, it will only render to this part. And other cool things which you can do with this GL viewport stuff is you can make multiple viewports. So what you can do is, I don't know, write 0, 0, width divided by 2, and height divided by 2, render something. Then you are going to again use this GL viewport. Now you start with width divided by height, then render something else. Then you are also going to just go down here and height divided by 2, and the last thing is width and the height divided by 2. What is going to result is making 4 parts of your screen. So like that, making 4 parts of your screen. So right here, the first one we're going to render here. So going to render here. So render something, we render it here. Then you are going to modify this and go to width divided by 2, so right here. And then the second render something else, going to render here. Then the next one will go upward and it will going to render here. So render something, this one going to render here. And render something else, the last one will going to render here. So you can have 4 different rendering, or however many rendering do you want, not just 4. At the same time, in real time. It's pretty cool. You should try it out. I'm not going to use this feature of the GL viewport right now to make multiple viewports, but it's a pretty cool thing. You should try it. I give you this challenge or exercise, whatever you want to call it. So this GL viewport function, let me go back to our original problem. We have this small screen, but this big texture, depth texture. So I'm going to use this viewport function to actually make sure that we render to the entire depth texture. This will be pretty simple, so let me just delete this and go here to the render. So rendering. By the way, this GL viewport is also useful when resizing the window. SDL windows defaultly don't resize, that's why we haven't used this GL viewport function. But whenever you resize your windows, like in GLUT or GLUT, OpenGL utility stuff, then you have to make sure that you set the viewport again to make sure that you render to the entire screen always. Default is this GL viewport is set to the size of the screen, so that is the default setting, and yeah, that's why we haven't used that. Although there is a way to make OpenGL SDL windows resizable with SDL resize constant. But let's get back to the original problem. We go to the display function, not in the display function actually, but we go into the get image from light position, and we are going to render to the entire shadow map. So I'm just going to use the GL viewport function with 0, 0 and shadow map width, and shadow map height. Alright, and let me set it back to the screen width and height at the end. So 640 and 480. I should probably make a constant for that. And let me try to run this. I hope I didn't screw this up. I did screw this up, definitely. Screw this up by using wrong names. Shadow map width. What did I call it? Shadow map width. Then it's probably a mistype. Not sure. Shadow map width. Wasn't the problem here? Let me go. 76 shadow map width. That's the problem. I created an integer shadow map width. Okay, I'm almost there. Shadow map height. The height, we have a problem with height, of course, because it's not capitalized for some reason. Okay then, let me try to compile this and now run this, and we should see less blockiness for the we don't see anything, do we? No, we don't. No, we see something, but but we only see them here. Why don't we see the shadow of this cone or whatever right here? Alright, I kind of figured it out. The problem was that all the frame buffer, all the texture which should be attached to one frame buffer should have the same size. So, as you may remember, when we have created this frame buffer object, we attached this render texture right here. And this render texture has the size 640 and 480. Now I wanted to attach another texture to called shadow map, but this shadow map has twice of that size, and that leads to a problem. Most likely, if I would have checked the GL check, I have called the GL check frame buffer status, then we would get some kind of error code or something which would have made it easier, but I didn't call that function, so it was a problem. But now, if I run this program, let me run this program. As you can see, we have the shadow, but it's less blocky. Let's try to even more increase this size. Let's try with an incredibly high value like 8. This is a pretty big depth texture right now, so it's a pretty high resolution depth texture, and it should probably make everything look much smoother. As you can see, it's much smoother with the soft shadowing or PCM, percentage close filtering, PCF. We will even make it a little bit better, but one thing which we quickly can fix is right here, right there. We don't have this kind of effect because, as you may remember, I put the camera something like this, so it doesn't actually have this part right here. And this is because right here for the texture I use this clamp to edge. So pretty much if it was lit at the edge, so at the border, not the border, but at the very edge pixel, then it's going to be lit. If there was shadow, then it's going to be shadow. A better approach is use GL clamp to border. This GL clamp to border will actually going to clamp to border, which pretty much should make whatever is outside of the frustum black. So if I just run this program, as you can see, whatever part is not inside the frustum is red right here a little bit, and right there a little bit. Okay, cool, we have finished most of the stuff which I wanted, so now we are ready to actually put some lighting. Alright, one more thing I want to do is that if your program, if your OpenGL program give an error for this GL text parameter, which I set somewhere right here, that GL text parameter, or you have a problem with the fragment shader with this function or this type, then let me go show you the other way to do that. Let me just copy this and make and comment this out, and this will be a shadow to sampler 2D, so no shadow in it. And you know, this is just a basic texture, you should already have that. Because every shader have that. And then right here we are going to comment this out, this shadow value, and going to make the manual solution, so the manual comparison. I'm going to create the same floating point value, so shadow value, and then I'm going to make another vec4. This vec4 will be called light vertex position 2, and this will be just equal to the light vertex position. And then we have to manually do something called a perspective division. The shadow 2D projection already do the perspective division, because it's right here it's right projection, so it's already do the perspective division. What is a perspective division? It's a very scary name, but basically you just divide the vector 4 by the W component, so make it 1. Let me quickly do that. So light position divided equal by the light position dot W. So this we are going to make the W position 1, and you know, further object makes further object smaller. This is what it basically is about. Then I'm going to use an if statement right here. This is where the actual test is. So I'm just going to use the texture 2D to get the distance of to get the depth in the depth texture. So I'm just going to use the shadow map as the first parameter, and this light position 2.xy. So I'm going to use the x and the y, so basically the screen position. It's not really the screen position, it's more like a number between 0 and 1. So this is basically the texture position. Normally it is between -1 and 1, so both the x and the y, because that's the normalized device coordinate. But as you remember, we use that bias matrix to transform this to 0, 1 range. Okay, and then I'm getting pretty much the R component, so I'm just using the .r. This is pretty much what this is about, I think. So this is what this that's not that. This is what this is about. So using the R, I think so. I don't really understand this why that parameter is needed. Okay, and then if it is greater or equal than the z position, then I'm just going to make this to 1. So like actually not this one, the shadow value equal to 1.0, else I'm going to make the shadow value equal 0.0. And let me comment out this free line right here, and let's try to recompile the program and see if it is going to give us the same result. So what I did is basically did what this function does automatically. First do the perspective division. You can Google it if you really want to know more about this stuff. It is happen usually automatically. Then if the value in the shadow map is less than the value which we have for the vertex, then it is lit. So the vertex is lit as in shadow. So this is basically just what I did here in GIMP a few days earlier. So if it is closer or equal, then it is lit. If it is farther away, then it's in shadow. So let me try to run this and see if the shader gives us a problem. No, it doesn't. And as you can see, we get the exact same result. Just to see, I'm going to change this to 0.5 just to see if the shader actually runs and we don't somehow get another value. And as you can see, it is actually running the shader. So this is the manual way to do so. Let me quickly do a percentage close filtering before we move on. How can we do a percentage close filtering is relatively simple. I'm just going to have the shadow value again, and using a 1.0, isn't it? And using a 2 for loop. So I'm just going to use for float x equal to some small number, x less than or equal to 0.01, and x plus equal 0.005, and then do the same. So float y equal to 0.01, y less than equal to 0.01, y plus equal 0.005. By the way, if you have watched my, so what is supposed to be, this is a 4, and that's right. By the way, if you have followed my post-processing tutorial, this is something similar than the blurring. So I'm just going to get values close to it. This is why it's called percentage close filtering, and then average them together. So let me just create this shadow value to 0.0, and every time we hit a light, I am going to add 1.0 to it. Now we should divide this with some number. So the shadow value is divided equal by how much it run. So it's run 1, 2, 3, 4. I'm not sure how much does it run. 0.05 to, actually this is minus 0.005, of course, obviously. So 1, 2, then it reaches 0, then it runs 1, 2, so it's 4 times 4, that's 16, isn't it? 16, 4 times 4 is 16. And then if I will just run this program, we don't actually need recompile, and we get nothing at all. Of course, we have to actually modify slightly the position right here, this position. So I'm just going to add a vector to it, vector 2, with the x and the y component, and this should slightly always modify the position of the current vertex. And there we go, we have some incredibly crappy percentage close filtering. In real percentage close filtering, you actually want to use pixels, use the size of the pixel to actually move with the size of the pixel. Probably if I will just make it to smaller values like this, 0.005, and let me add one more to it, then we will get a little bit better, if you can see that. Try to use a pixel size. Again, this is a kind of exercise for you if you really want to try some exercise. And now that we have this, we can probably go into and creating a shadow, because we have the basic idea. We have a shadow value. So creating lighting is as simple as getting the light to work, the per fragment light, and multiplying the result of the diffuse and ambient light with the shadow value. So we get very dark places and very light places. Alright. Alright, well, we all pretty much have everything which we kind of needed. As you can see, we have the shadow map, and we have kind of a soft shadow right here. We have changeable size in the shadow map, so we are pretty much ready to go. One last thing is to add the actual light, because we have just outputted black or white pixel depending on if the current pixel is in shadow or not. This will be fairly simple since we already implemented the per fragment lighting right here in the fragment.frag and in the vertex.vs. So with the help of these two files, we will going to finish this up quite quickly. So let me just use this vertex.vs, and I'm just going to copy this entire thing to the vertex shader right here to the bottom. And let's see, what do we need here? We need the normals, so I'm going to copy that right there. We need the normals. We don't actually need we don't need the color though. We need the color. Let's see, I don't think that we need anything other from here. We need the out color, because we want to just send colors as well, though currently there are no colors with our simple scene. Everything is just gray. Let's see, we need this position. If you don't remember, this position was in the past the vert position of a simple vertex. This is how we did the color. This is something which is needed for the calculation right actually here, where we actually just calculate where the light is. So this is the surface to light. Yeah. Okay, we need what do we need? We need the out normal, and oops, that wasn't the control X. We know the out normal, and that's pretty much all the varying variable which we do need. Let's see, do we need another uniform matrix? Not for now, so I'm just going to delete that. And I'm pretty much just going to copy, let's see, yeah, about this part, except the tangent. I will delete the tangent. We don't need tangents right here. And yes, that should conclude it, although there will be one more thing, which is the light, because the light is static in the screen, and this will have a separate matrix right here, so uniform and mat4, and I just call it light matrix. You will see in a moment what this light matrix is, but this is pretty much just the model view matrix. Actually, we don't have a model view matrix, do we? Nope. So let me just copy it, because we use model view matrix to move to vert position. So this light matrix is just the vert position, the vert matrix. So the model view matrix for the light's position. So let me just make another varying variable. This is a vector free, and I just call this light position. Okay, and we also need an input light position, which will be a uniform variable. So I'm just going to put it right here, uniform, and this will be called, this is a vector free and light position, but this is the inline position, in light position. So this position right here is in model space. So, and this light position right here, this is in world space. So this is what is needed to make the light static. So far, whenever we did lighting, let me just open up some program where we did lighting. Yes, we did it here. So if I just open this up, actually the light comes with wherever I go. So if I go here, the light is here, because the light is basically about the same place as the camera. So it's not static like this monkey object that whenever I go, it stays the same place, but it's coming with us. And that is because I directly use the position of the light in the light calculation without multiplying by the model view matrix. So if I'm just going to create a model view matrix for the light, and I multiply it with multiply the light position with that model view matrix, it's going to stay at the same place, just like the monkey. So if I move to the back, I would see that the back of the monkey is black, basically, because the light stays there. So this is what we are going to achieve by multiplying by the model view matrix. So let me actually write it here. This is the model view matrix for the light. Okay, what do we need? Actually, let me put this varying variable right here at the bottom. So we have nice groups. We have attribute group, uniform group, and varying group. And that's pretty much conclude the vertex shader. I'm pretty sure we have to one more thing. One more thing is to set the light position. So the light position is equal to with the multiplication with the light matrix, which is the model view matrix for the light, and I multiply the in light position with that. But the in light position is a vector free, and the light matrix is a matrix 4. So let me just cast nicely this to a vector, 4-dimensional vector, and then cast this back to a 3-dimensional vector. Cool, we have the light position in vert space, meaning that it will be static. So let me go to the fragment shader and let's see what do we need to do. Again, I'm just going to copy the fragment shader of the original lighting and copy it down here, and we will see what do we need. We need most of these varying variables. Let me just put the varying variable to right here. And we need the normal, we don't need the tangent, need the color, don't need the UV. Need the light position, and actually this is not out light position, this is just a light position. What is called light position? Okay, light position, and we need this position right here, which is right here, which is the vert position of the vertex. Cool. Let's see, we don't need textures right now, but we need the camera's position. So let me just put it right here, camera's position. We need the light position, we don't need that, but we need the color of the light. By the way, I'm not sure if we actually implemented it like that. I think we used a load of uniform variable to set the color of the light, and now I just put it here as a constant. Why isn't it colored? Constant and vector free should be colored. Anyway, so yeah, I'll just put it here as a constant, so we don't have to worry about that. I'm not sure if this is the same program as we have used earlier. Okay, and right here I'm just going to put the entire thing, so this entire light calculation right here. So let me just cut out the entire thing and paste it right here. This is calculating a lot of stuff, and we don't have to care about what this is right now, though this is called light position instead of light pose. Position, normal. Let me increase this a little bit so we have a smaller specular dot basically. And the fragment color will be not calculated like that, but let's see if let me think. So the light will be calculated like this. We have this shadow value, which is a number between 1 and 0. So we have the ambient light, that's for sure. So I'm just going to write ambient plus, because whether we have shadow or not, the ambient light will be always applied. Then I'm going to have shadow values multiply by the diffuse contribution multiplied by the diffuse light, so diffuse color. Actually this first one is called ambient color. Ambient color. We put a space right there. Okay, and not even there, but somewhere here. So we have the ambient color, we have the diffuse light. By the way, this is how we calculated it, isn't it? Okay, let me just copy this one. That will be quicker slightly. Okay, so the ambient color times out color, we always have ambient light. Then we need to multiply this by the shadow value. Shadow value. So if it is 0, then we don't have diffuse light at all. If it is 1, then we have, but actually not multiplied by shadow values, but let me add a little bit of contribution to it, like 0.01 or maybe a little bit higher, 0.05, just to make sure that we have some very small diffuse value. And then we have right here, we multiply this by the shadow value. Shadow value. Or even better, if the shadow value is less than, I don't know, 0.5, then I don't have specular, else, so then 0, else I have the normal specular multiplied by this shadow value. Something like this should do the trick. So I'm basically getting ambient color, doesn't matter if the current point is in shadow or not. I have a small diffuse color even if it is in shadow completely, but I don't have specular light if it is in shadow. Okay, we have to fill these variables in, and this tutorial should conclude then. So let's see what do we need. So in the display function where we have the shadow shader, we have to fill up each of these uniform variable which we have given. Oops, this is not our file, we can escape from there. So the vertex shader, let me see what do I need. We need the light matrix, I will care about a little bit later. We need the light position, so let me just pass this light position with the GL uniform function. Probably I can copy it from somewhere, GL uniform free f, because it's a three-dimensional vector. And then I need to get the in light position. and we have already a vector for that, if you remember, called light position right here. So we use this light position and pass the components right here, x. Oops, that was y. Never mind. So I just pass the x, y, z right there. Perfect. Then let's see what else do I need. That was all uniform value except this light matrix, which we are going to fill up in a moment. Then I have this camera position. The camera position can be easily get from the three-dimensional camera which I use. Camera position. So the camera position is, we can get it by cam.getLocation.x, and similarly do the same trick with y and z. Z and y. Okay, we filled out the camera's position, and that's all. That seems not as much as I have remembered. Don't we need anything else? Huh, it seems like we don't. So let's fill this in light matrix up. So let's fill this light matrix up. This light matrix is a four-dimensional, so 4x4 matrix, four-dimensional matrix, which is storing pretty much the position of the light, so model view matrix of the light. How can we get that? Right here, I'm going to get that here. Get model view matrix for the light. So I'm just going to put the calculation right here. We have to get the view matrix because obviously to be able to make model view matrix we need the view matrix. So to get the view matrix I'm just going to make a mat4, a 4x4 matrix, and I just call it view matrix. I hope it doesn't actually conflict with any other names, and I'm just going to use the pipeline dot get view matrix. Perfect. And then we need to actually do a pushing back. Wait a moment, I will explain it in a moment. So push back and make sure that we are actually in model matrix. So pipeline dot matrix mode and model matrix, because we always want to be in model matrix except when we deal with the camera. Okay, so I'm setting the matrix mode to model matrix, and I'm pushing back the matrix, and before I forget, I'm just going to get it. So pipeline dot pop back. So we will test out if this pushback pop back is actually working. Then I'm just going to move the position. So I'm going to use translate. So pipeline dot translate, and I'm just going to translate to the position of the light. Right here, the position of the light. And I'm going to get the model matrix right now. So glm mat4 and model matrix. The model matrix is just simple, the pipeline dot get model matrix. Perfect. And then simple, this matrix, the light matrix, will be basically multiplied together. So glm mat4, and I just call this light matrix equal to the multiply the model and the view matrix together in the opposite order. So view times model. And this should do the trick. So I'm just basically getting the model view matrix of that position where the light will be. And then I calculate this light matrix. So I just need to give this light matrix to the shader. So light matrix, and right here light matrix as well. Okay, I think this should do the trick. Let's try it. Okay, we have a slight little problem. No member called pushback. I'm pretty sure we have implemented pushback, or we didn't. Oh, we have push matrix. Well, anyway, just quickly then rewrite it to push matrix, and I guess then the other one is pop matrix, but I can simple check this if I wouldn't close that up. So we have a push matrix and we have a pop matrix. Alright, I can live with that. I have a little mistype in 205 pipeline. That's right. Anything other? It seems we have get model matrix. We have a capitalization issue right here. Should work right now. And then of course we have to debug the shaders as well. It's not enough that our program compiled, the shader needs to be compiled as well. So we don't actually pass the normal matrix right here. So we can quickly change that. So uniform mat3 normal matrix. The normal matrix is either just a 3x3 part of the model view matrix, or the transpose inverse of the other matrix. And line 42, float to vector free. Oh, this is a vector free 0.0, 0.0, and 0.0. So basically that's defining the black color there. Let's see. Doesn't seem to work. This specular light shouldn't moving with us. I think so. Or is it okay? It can be okay. I don't know. Seems weird though. No, I think it's okay. Just some reason we have a huge specular light, so let me just change this, I don't know, 32 power, so we have a smaller specular dot. It's a little smaller. I don't know. It might be working. Seems weird though. I think it's working as it should be. And as you can see, it actually solved some of these issues with the back faces, because the diffuse light actually making the back face black, so you then actually see those patterns right there at the back. And let's see, what else do I need. Of course, I should show you how to make a rotating object and moving object with it, because I only said that you have to update the matrices in order to make moving objects to actually work. So let me actually demonstrate it. I'm going to load up another scene, so I'm just going to use this, what does it call, mesh loader, and I'm just going to call this monkey. This monkey head will load the monkey object which you have seen at the beginning of this tutorial, which is mesh loader, the test.obj, I think so, the test.obj, and right here at the end we should delete the monkey. So right here we need to actually do a little bit of trick. I'm going to create an angle. I don't think that I do have an angle, which pretty much the rotation of this monkey head, so angle, and this is start from 0.0, and somewhere in the display function, or pretty much anywhere where I want, I'm just going to add some value to it, so 1.0, and then is the angle, if the angle is greater or equal 360, and I'm just going to go back to near to 0, so minus equal 360, and in this way we don't have too big of a value, so we don't have to worry that much about the floating point precision. And then I'm just going to draw out this monkey head. So right here I just draw out the scene. Actually, let me first show you what would happen if you just simple draw out the rotated monkey. So get image from light position, and I don't render just the scene, but I'm going to rotate it right here. So pipeline.rotate, and I'm rotate Y, and I'm rotating this monkey head with angle, and I'm just going to call the draw function of this monkey, so draw, and I'm just using this. Of course, I render it here, and I should also render it not only here, but here in the other position where I actually render the shadows thing, except this time with a shadow shader. And let me just show you what would happen then. Okay, the angle was obviously declared somewhere right here. And actually, I don't only translate it, I don't only rotate it, but I apply a little bit of translation. So right here, I'm just going to call the pipeline.translate, and I'm just translating 1, 2, 3. So it will not be on the center of this entire plane, because that looks plain ugly. And right here as well, so translate and rotate. And if we start the program, we didn't actually translated it because we didn't update the matrices. We have to update the matrices between every drawing call, which should update the matrices. So let me just quickly search for an update matrix right here and copy it after there. Usually it happens automatically with fixed matrices, and I don't actually kind of used to always having to manually do that, so I sometimes forget to update the matrices. And pipeline that update matrices, I just call it here, but this is not what I wanted to show you. What I wanted to show you is that it will not have the red shadows without updating the shadow map. So right here we have this monkey object. It doesn't have actually smooth normals. And we don't actually see its shadows right here. The shadow should be right there if it would work correctly. And it's not working correctly. It's really annoying that it doesn't have smooth normals. So the shadow should be somewhere. Now I get why we didn't see the actual monkey. That's because right here in this get image from light position, we never actually changed back to model matrix. So let me just go down here and change this to model matrix. And if I try to compile it now and run this, we see what I actually wanted to show you, that it's not working correctly. So although, as you can see, we have some kind of moving shadow, and we actually have the moving monkey object, the shadow seems pretty weird. So this is not how the shadow should look like. If I just come here and go up, you can see we still see the shadow, and we shouldn't see that. That's because we don't update the shadow matrix with every call. So let me actually make a function which is going to update this. This will be right here. This is void, and I just called update shadow matrix. Update shadow matrix will be a pretty simple function. What it's going to do is basically this, almost this. It's just going to get the model matrix again, because that's the only matrix which can change, and calculate the shadow matrix again. And also it's going to send it to the shader. So I'm just making an unsigned int right here, call this shader ID. So this shader ID, and I'm going to send the shadow matrix to the shader. We don't actually need to get the view or the projection matrix again, well, because these are not changing, only the model matrix change by using translate and rotate and similar functions. Okay, and I calculate the shadow matrix again, and let me copy the line which updates the matrix, so this one, and I'm just going to put it right here. And I'm just going to use the shader ID right here as its first parameter. Okay, seems good to me. Although one thing, this model matrix should be global, and also the model, view, and projection matrix should be global, because obviously we need to use the view matrix which we get here, and yeah, that's pretty much it. Making these and deleting these. X. So what I'm doing is basically using the view and the projection matrix from the get image from light, but updating the model matrix depending on where we translated. And then I'm just going to call this update shadow matrix everywhere where we would draw something. So for example right here, and I'm just using the simple shaders ID. Okay, I'm going to call this again when we draw the monkey. I'm going down here, call this again when we draw the scene with the shadow shader, and I'm going to call this again before I draw the monkey. So let's see how it's going to work. I don't know. I hope it will work well. So if I run this, and seems better than previously. We don't have those weird shadows, as you can see. It's working as it's supposed to work, except for that not smooth normals, but the shadow is updating correctly, and we have, and that's pretty much it. That's pretty much what I showed you in the first demonstration video, isn't it? There is nothing else in here which should be stated, although there are a few things for which is not really a part of this tutorial but going to be part of a later tutorial on advanced shadowing, because so far we have one directional shadow, and that's not really one most of the time. You want a lot of shadows and stuff like that. So the trivial solution to make a lot of shadow would be to use another matrix, so another light model view projection matrix. I just call it light model view projection matrix 2. Use another shadow map right here in the fragment shader. I just call this shadow map 2, and yeah, it pass another varying variable which is light vertex position 2 or something, and you know, do the entire calculation again and add the shadow values together from all of the light. Of course, that's a working solution. You can either use, I'm pretty sure you could use arrays, maybe not, I'm not sure, but for the matrices you definitely can use arrays. So I don't know, making 10 lights and something like that to make a lot of lights. That's what I want to demonstrate. I hope I didn't actually screw up our shader. No, still compiles. And let's see what else should I mention. So this is the trivial way to create multiple shadow casting light source. I leave that to you as an exercise if you want to. But creating a lot of sampler right here, a lot of sampler and a lot of texture is not a good idea, because older hardware, like for example mine, can only handle at max 4 texture, input texture layer if you would like. And yeah, that's actually a problem, because you actually need not only shadow casting light, but you actually need a lot of kind of texture, and you only have 4 texture layer which you can use. So what you could actually do to avoid this problem is creating one big texture. As you can see, this is one big texture, I don't know, 2049 by 2040, actually 48, that's 2048 by 2048, so it's a huge texture. And you could, with some clever tricks, could make up 2024 textures right here. You could right here build up 4 256, no, this is 512 by 512 texture, and you could actually build up, that's not the right number, I wanted 8 here, so let me just do it one more. So you can build up 8 256 by 256 texture, and with it you can use only one texture and make a lot of shadow maps. Of course, you have to tell what this part stands for, what this part stands for, so what light. And with some clever algorithm, you have to assign the closer light here to the bigger texture, and the far away light should be assigned right here to the smaller texture, because we don't care about small light. A few pixels is the entire light, so we don't actually have to do 2 big shadow maps for that. And with GL viewport, you actually assign to each part and somehow remember that, add it to the shader. Maybe some later tutorial, an advanced shadow mapping tutorial, we will implement kind of like this algorithm. Also, the point light or omnidirectional light is another question, which is pretty much made up, the simplest approach, by 6 normal texture. So if you have right here point light, then you just make one texture right here. This is 90 degree, and take an image there. Then take an image there, and take an image there, so upward, and take an image downward, and take an image toward me, and take an image from me, and that will define basically a cube map, 6 texture. And from that you can build up an omnidirectional light from 6 normal lights. Let's see what else should I mention. That's pretty much most of the stuff which I wanted to mention. You can play along with these numbers, or you can add some bias to right here. A little bit of bias will be to actually subtract some value from this one. If you're subtracting some value from this one, that will cause that some of those self-shadowing problem will actually disappear. And the Moiré pattern, for example, will disappear, but it will also going to create shadows which are not really connected to the body, which casting the shadow, which is not too realistic. But as long as you don't use too big numbers, so like minus 0.0001, that will not be noticeable. So try to play along with these numbers. And yeah, this was a long tutorial, so I should conclude it right here. Thank you for watching, and have a great